Morning, everybody. Doing okay today? Yeah? Good. I have a few exams that people didn't get, so if you didn't get your exam, you can pick them up after class, okay? The exams I did post them online, so if you want to look at them, you're welcome to. And if you have any questions about it, remember that our next exam is not for a little while, but we will have a quiz. When? Today? Thursday. Yeah, we'll have a quiz on Thursday. And then, I guess, we're just going to have another quiz on Tuesday, huh? What do we do? Class. Yeah, this morning our break, so no class next week, but we'll be back here on Thursday. Right? We come back on Thursday? Yeah. We won't have a quiz next Thursday. We'll wait till the following week. But we will have one this Thursday, day after tomorrow. And that'll cover pages, I've put an announcement online, I think 92 to 102. That's the last part of that chapter, the physics of the body chapter. Any questions? Concerns? Oh, goodness. It's not due till the end of the semester. Later, we'll talk about the project more. I'll have you sort of brainstorm your ideas. You don't need to be thinking about it right now. Okay? If you want to, you can. It's not due till the very last day of class. You can chat with me later if you want more ideas about it. Okay? So let's pick up where we left off. Remember, we were talking about closed versus open systems. And closed systems are systems where no energy can go into the system or come out of the system. And then open systems are where you can have energy that comes in and out of the system. So in a closed system, the total energy will remain the same. And if a system's not closed, then we can we can always enlarge the system, just incorporate more and more into the system until it becomes a closed system. Because the universe is a closed system, right? There's no energy coming in or going out of the universe. And so if we make the system as big as the universe, then that's going to be a closed system. So for example, let's imagine that we have a bicycle. See if I can draw a bicycle. It's got two wheels. That's sort of a bike, right? That's not very good. Anyway, if I have a bicycle and it's moving, then something would seem strange about that because I have energy that is somehow coming into the bicycle and causing it to move. But a moving bicycle is not a closed system. Like if I'm just thinking about the bicycle, kinetic energy appears. Somehow, mysteriously, we don't know how, but somehow the bike gets kinetic energy, and that causes the bike to move. However, if you include the rider, that's a guy on the bicycle. He's pedaling the bicycle. So if you include the rider, then it becomes obvious, where the energy is coming from. That the rider is providing the energy to the bicycle. And in that case, the system would be closed. Because I don't have any energy that's going into the system or out of the system. Everything is contained within this box. All the energy is coming from the guy, and the energy is causing the bike to move forward. The energy is converted from the man's muscles, which gain, of course, energy from the food we eat. As I said, the universe is a closed system. I might ask you just some basic questions about what an open versus closed system is. Open system, energy comes and goes. Closed system, energy doesn't go in or out. And then I might give you an example like the man on the bicycle and ask you, is this an open or a closed system? And you'll be able to tell because is it getting energy from somewhere? And is that source of energy part of the system that I'm talking about? So like the moving bicycle, not closed because it's getting energy from somewhere that's not part of the system. But the man on the bicycle, yes, closed because the man, which is providing the energy, is part of the system. Okay? Now, let's look at power. Power is the rate at which work is done. We'll see power again when we do electrical energy in a later chapter. But right now we'll just define power as work over time. Or, remember the work energy theorem, we can also think of it as energy per time. And so when I think about the units, well, what are the units of energy? Do you recall? Units of energy? Huh? You're right. Yeah, it is Newton meter. But we also, joules also. So I'm going to use joules. So it's joules over seconds. 1 joule per second is the unit of energy. Do you know what is the unit of power? Do you know what is the unit of power? Is what? Did you get that? Do you know what is the unit of power? Nobody got it, did you? Y'all don't have a very good sense of humor, unfortunately. Oh, yeah, fine, sense of humor. 1 joule per second is 1 watt. And we abbreviate the watt with a capital W because it's a person's name. All right, you're familiar with watts. 100-watt bulb, 1,000-watt hair dryer. That's a measure of how much energy per time those devices use. And efficiency describes how much energy is converted in a particular task. And efficiency is equal to our power output over our power input. So it's a ratio of our output power to our input power times 100 and makes it into a percentage. Right? You hear of things saying, oh, this is 50% efficient, or this is 80% efficient, or this is 120% efficient. Right? Have you ever heard of those? You've heard this before? 120% efficient? Because you know what that means? Like if something has an efficiency that's more than 100%, that means that it's putting out more energy than it's getting in. So that doesn't happen. But you have heard of things in their efficiency that they can have a 20 or 30 or 50% efficiency. You can also give this in terms of work. It would be the same. It's the work output over the energy input, or the work input, we can think of those as the same, times 100%. So let's imagine that I put, I don't know, 100 joules into a system. So my input energy is equal to 100 joules. But the energy that I get out is only a fraction of that. Let's say that I get, I don't know, my work output is 30 joules. Then what is my efficiency of that system? What's the efficiency of that system? Well, I would say 30 over 100 times 100%. And so that would be a 30% efficiency. You'll have an efficiency problem, but I'll try to make the numbers really simple. I just really want to know that you understand what efficiency is. I'm not looking to see that you can do the numbers correctly. That you can deal with, big numbers. Now, here we have 100 joules in and 30 joules out. So that means that somewhere along the way we lost 70 joules of energy. Where did that energy go? Where does energy usually go? Where?
Out as heat.
Yeah, out as heat. Yes, yummy, good thing. So it goes out as heat, right? Like in your car, when you're taking chemical energy from the gasoline to turns into thermal energy, which causes your pistons to move. We get a lot of energy that goes into the car, but there's a heck of a lot of energy that goes into the engine, just the heating up the engine. That's basically lost energy. So most of this stuff goes into heat. Most of the lost energy, some of it will go into sound, and then some of our energy will go into gravitational potential energy or kinetic energy. Remember, we used different variables for this earlier. We used a U and a K there. Let's try some of these these questions. An engine has an efficiency of 20%. It produces an output work of 20 joules. How much energy was lost? So the output is 20 joules, and it has a 20% efficiency. How much energy was lost? And then my next question will be, how much was the total amount of input energy? The output is 20 joules. Right now I want to know how much energy was lost. You are near perfect right now. Only one person has, two people have the wrong answer right now. Okay, a few more. But ask a neighbor if you like. All right, let's stop at 108. 108. Okay, it's been thinking a lot lately. We'll come back to it. I'll show you what your answers were. Most of you got the right answer. The answer is 80 joules. And so if I were to ask you how much was the total amount of energy put in, what would you say? 100 joules, right? I put in 100 joules, I lose 80 joules, and I get 20 joules out that's usable. So if I go back to my equation, the way that I would do this is I would say that my efficiency, which is 20%, is equal to the work out, which is 20, divided by my En times 100%. That's a percentage sign there. And I want to know what En is. Well, I can cancel out the 20s here and here, and that leaves just a 1 on that side. So I'm left with 1 is equal to 100 over En. So that means that the input energy is equal to 100 joules. And you might be inclined then to put D, but be careful because I'm not asking for what is the input energy. I'm asking for the energy that's lost. And so in this case, I lost 80 joules of energy. Let's see if I can show you answers now. Yeah. Oh, goodness sake. I'm going to tell you a joke. I think I did really well. How do you get a baby astronaut to go to sleep? You rock it. All right. There we go. All right, B is right. Okay, where does this lost energy mostly go? In almost every case, most of the times, where does the lost energy go? All right, let's stop at 28. 28. Okay, awesome. Hey, why didn't the son go to college? Because he already had like 1,000,000 degrees. The sun, the capital S sun, like S-U-N. All right, so the energy loss mostly goes into heat. With that said, let's talk about temperature and heat. I want you to be familiar with the 3 temperature scales. You're probably familiar with, well, you're probably not that familiar with them. But I want you to be familiar with the Fahrenheit scale. Fahrenheit, it's German, means like to drive, Fahrenheit, heat. The Fahrenheit scale, so the Celsius scale, and then the SI unit for temperature, which is neither Fahrenheit nor Celsius, which is the Kelvin scale. you need to know what these are based on, and you need to also know the Fahrenheit and the Celsius. What are some common temperatures in those scales? The Fahrenheit scale, for example, or the Fahrenheit scale, the freezing point of water, we know, is 32 degrees Fahrenheit. The boiling point of water is 212 degrees Fahrenheit. And for the Celsius scale, it's a lot easier. The freezing point is 0 degrees Celsius, and then the boiling point is 100 degrees Celsius. So both of these scales are based on the freezing and boiling points of water. That's how they set the size of the degrees. And anytime you have a scale, you have to have one known quantity, and then you have to have another known quantity. And then where those two known quantities are, they set how big the degrees are in between them. So for example, here, this is our Celsius and our Fahrenheit scale. My freezing point is right here, and my boiling point is right here. And in the Celsius scale, we just put 100 right here. And in the Celsius scale, we put a 0 right here. In the Fahrenheit scale, we'll label the freezing point at 32 and the boiling point at 212. And then we set all the other degree marks based on those two quantities. So which is bigger, a change in 1 degree Celsius or a change in 1 degree Fahrenheit? Let's try that as a question. Which of these is bigger? If I have a change in 1 degree Celsius in our temperature and a change in 1 degree Fahrenheit, which of those is a bigger change in temperature? Celsius or Fahrenheit? All right, let's stop at 30. 30. Man, you are killing it today. Good. So A is the right answer, the Celsius, because I only have 100 tick marks between 0 and 100. But over here, I have almost twice as many. I have a lot more tick marks between 32 and 212. I have 180 tick marks between 32 and 212. And just so that the size of the degree over here is bigger than the size of the degree over there. Okay? They're two different scales, but they're both based on the freezing and boiling point of water. You can convert. I'm not going to ask you to do this on the test, and you don't need to know these formulae, but I just want you to be familiar with them, just to show them to you once. You can convert between the two different scales. In fact, I think these might be on your equation sheet. A Fahrenheit temperature, if I want to know what, if I have a Celsius temperature and I want to know it in Fahrenheit, it's 9/5 of the Celsius temperature plus 32. And if I want to know, if I have a Fahrenheit temperature and I want to know it in Celsius, it's 5/9 of TF minus 32. So for example, let's say that I want to know let's do this. I want you to also know what are some common temperatures in the Celsius scale, because most of us aren't really familiar with the Celsius scale. So I want you to know what is room temperature. And I also want you to know what is body temperature in the Celsius scale. All right, room temperature is about 70 degrees Fahrenheit. You might know what that is in Celsius. It's about 20 degrees Celsius. And body temperature, you're right, it is 37 degrees Celsius. And I can do that with this. Like I can take my Fahrenheit temperature, 70-ish degrees, and I'll get a Celsius temperature that's around 20 degrees Celsius. Or I can take my Fahrenheit temperature, 98 point whatever, and I'll get my Celsius temperature of 37. So I would say, for example, 5/9. My body temperature I know is 98 degrees Fahrenheit minus 32, and this would equal to 37 degrees Celsius. All right? just so that you're sort of aware of some common temperatures that we encounter in the Celsius scale, because it's not something that we use very often. You don't need to worry about converting 70 and 37. I also want you to know about the Kelvin scale. We okay on the Celsius, Fahrenheit scales? We good? Know what they're based on, freezing, boiling points of water, know how the scales are different, and then know some common temperatures. I want you to know the Kelvin scale, what it's based on. It's different from the other two scales. It's based on absolute zero and the triple point of water. So it is a scale that at the bottom we have absolute zero, and we call that 0 Kelvin. And then up here we have the triple point of water. I'll describe what that is in just a second. And we list that at 273 Kelvin. Okay, absolute zero. We talked about this before. Remember the video with the British guys? And they were doing the liquid helium thing? They were talking about how the closer and closer it gets to absolute zero, the less and less the particles move. The atoms, theoretically, at absolute zero actually stop moving. And nobody's ever reached the limit, but they've gotten really close to absolute zero. I mean, even in fact, over in one of our instrument rooms, we get pretty darn close to absolute zero, on the order of, I don't know, millikelvin or microkelvin, just a little bit above absolute zero, because liquid helium is pretty cold, liquid helium. But at absolute zero, then you have a point where all the atoms just stop moving completely. Everything stops. Remember, because temperature, thermal energy, is really just the motion of particles. And then the triple point of water is the point where water exists in all three phases. You know what the phases are, right? Solids, liquids, gas. At the triple point of water, water is a certain temperature and pressure where water exists in all three phases. Let's write that down. So, triple point of water is where water exists in all three phases. It's just a little bit above the freezing point of water, the triple point of water. I think it's like maybe 1/100th of a degree Celsius or 1/10th of a degree Celsius above 0 degrees Celsius. So just a little bit above the freezing point of water. And when you have it at a certain pressure, then you can get water existing as a solid, a liquid, and a vapor all at the same time. That's kind of cool, no? You can have water existing in all three things at the exact same time. And then absolute zero is where all motion stops. I do want you to know what those are, absolute zero and triple point of water. But more importantly, I want you to know that the Kelvin scale is based on those 2 points. The Fahrenheit and the Celsius scale, boiling and freezing points of water. The Kelvin scale is based on the triple point and absolute zero. Now the Kelvin degree is exactly the same size as the Celsius degree. In fact, the two scales are just offset from one another. They're not actually, they're not different kinds of scales. They're just offset by this 273 Kelvin. No need to worry about that right now. Or at all, actually. Okay, we good with this so far? Understand what I want you to know? Okay. All right, heat is the transfer of thermal energy. Goodness bless you. It's the transfer of thermal energy. You remember in that video, the guy said, remember the video with the British guys, that you can't get to absolute zero, because in order to get to absolute zero, what you have to have is something that's colder than absolute zero. You aware of what I'm saying? You know, when we cool our houses, the way we cool our houses is we put something that's cooler than the rest of our house in our house. And then that draws heat away from our house. You always, if you want to decrease the temperature of something, you have to have something that's colder than the temperature that you want it to decrease to. Because we have this transfer of heat that will move from one object to another. And that's why you can't get to absolute zero, because in order to get to absolute zero, you'd have to have something that is actually colder than absolute zero. And that doesn't exist. Right? So when we're talking about heat, we're talking about this transfer of thermal energy. The total amount of energy inside an object depends on the type and amount of material. This energy is called thermal energy. So heat and thermal energy are related, but they're different too. That heat is the transfer of thermal energy going from one point to another. But thermal energy, if we look at a substance, it's the total amount of energy that's wrapped up inside of that substance. And it's dependent upon how quickly those particles are moving around inside the substance. All right. Thermal equilibrium occurs when there is thermal contact. So if I have two objects that are in thermal contact, those two objects are able to transfer heat. You don't have to be touching in order to have thermal contact. That you can be in thermal contact with something in other ways too. Like we like to go camping. You like to go camping? Anybody? Really? Anybody else? Just you and me. Yeah. So when you go camping, you build a campfire, right? You like campfires? Who doesn't like campfires? Yeah. Anyway, when you build a campfire, you make marshmallows because you make s'mores. But if you take that metal rod and you jam it into the fire, now marshmallow forks today are a lot better than they used to be. But used to be, it was just a piece of metal, a coat hanger. Eventually that coat hanger is going to get hot because you're in thermal contact with the fire. You're sticking one end of the coat hanger into the fire and you're holding the other end of the coat hanger. And so that heat you get heat that transfers from the fire to your hand. And eventually it'll get hot if you drop it down. Marshmallow forks today, they have handles, they're extendable, they sort of have this complex network of wires that sort of limit the amount of heat transfer that you get. They're quite complicated devices, are they not? Yeah. Or a stick is always good too. The thermal equilibrium occurs when there is no flow of heat between the two objects. And this only occurs when you have the same temperature. My daughter, whom I love, she's awesome, I love her a lot, but she, in the wintertime, she always complains about her bed because she has, a sheet like most people, and then she doesn't have a top sheet, she has a fuzzy blanket on the top, like one of those, what do you call them? A fleece blanket. She has one of those blankets. And so in the wintertime, she doesn't sleep underneath her fleece blanket. She sleeps on top of it. And then she pulls another blanket on top of it. Because she says that the sheet is too cold. Can you tell me what's wrong with that? Is the sheet too cold to sleep on? Have you ever gotten into bed and you feel like, gosh, the sheets are really cold? What's wrong with that in the context of what we've just said? Are the sheet and the blanket in thermal equilibrium? They're sitting there, they're touching all day long, the sheet and the blanket, snuggling up next to one another the entire day, throughout the day, no matter how cold it is. They are different materials, but they're in thermal equilibrium. Well, let's look at this. So I have.
I had it in my inbox.
We got two things here. I want y'all to see. But I'm going to ask a few of you to touch them. They're not toxic or anything, but just touch them and tell me which one's colder. Which one's colder? The one in my right hand. Which one's colder? The one in my right hand. She agreed. The one. Did I give you more, or y'all agree? The one in my right hand is colder. Huh? You want to feel? This one is colder, they say.
Well, I feel like that one feel like
Wood. So I have a thermometer. This is an infrared thermometer. You know, when things have a lot of thermal energy, they put off infrared light, and this measures the infrared light. We'll talk about that when we get in the infrared chapter. And so, if I turn this on, see, it has a little laser, but that's just to tell you where to point it. Really, it has an infrared detector. And so my hand is about 24 degrees Celsius, or 75 degrees, 78 degrees Fahrenheit or so. All right? Because, you know, your appendages, they're cooler. The surface of your skin is not at 98.6. All right, this desk right here is about 69 degrees. It's pretty much the same temperature as the room. The floor is a little cooler. It's at 63 degrees. Well, let's look at these guys. These have been in that bag all day long. All night, they've been sitting up there, snuggling up next to one another. And this one is 67.8 degrees. This is the one that was in my right hand that was colder. We'll see about that, Dee. $68 degrees. Actually, this one is 68 too. They're both 68 degrees. But they seemed a lot colder, didn't it? Right? You agree? But they're in equilibrium. They're in thermal equilibrium. And when you're in thermal equilibrium, you have exactly the same temperature. Let's do something else, because this really gets to why Ada is all wrong about her sheets. And let me show you something. I might want to get up. Can you see over there? Let's stand up. You know, see? It's kind of cool. So this is the one that was hot, and this is the one that was cold. But we know really that they are, you know, see? Drew, see? You can't see over there. We know that, actually, no, look, I can put it on. Okay, or maybe not. I'm sorry. Cold, hot. You ready? I'm going to put some ice on it. Now, which one do you think is going to melt faster? Or will they melt at the same rate? The one that's cold, the one that's hot, or will they be the same? What do you think is going to melt faster? The same. They are the same temperature, right? They're both at 68 degrees. So as long as they're staying up, that's reasonable. But the one is hotter, right? So which one do you think is going to melt faster? Are the same. They're right, the same. Adam? True? Okay, so let's see. This one's the hot one, and this one's the cold one. You ready? And this one's the cold one, and this one's the hot one. Hot, cold, hot, cold. Hey! Look, this one's not doing anything. And look at this one. Oh, it's almost gone. Now see? Look, it's water. And this one is still ice. So what's the difference in these two materials? Such that this one is plastic, but yeah, you're on the right track. What's the difference between the wood and the metal? And the difference between the sheet and the fuzzy blanket? Right, but what's the difference in the material? Yes, yes. So one of them is a really good conductor, and one of them is not. So the fuzzy blanket and the sheet, they're exactly the same temperature. The difference is, though, is that one of them is a really good conductor. So it's aluminum, right? This aluminum block, I touch it, and it feels really cold. But the reason is that it's a really good conductor of heat. And so what it's doing is it's drawing heat away from my hand very rapidly. And that's why it feels cold, because it's drawing heat away from my hand. But this one, which is also 68 degrees, is not a very good conductor. It's a good insulator. It's plastic. And it's not drawing heat away from my hand. So it feels a lot warmer, even though they're exactly the same temperature. And so the sheet and the fuzzy blanket, like which one are you going to sleep on in the winter time? Are you going to sleep on the fuzzy blanket, or you get down in between them? I don't know. I don't really want to know which other you sleep. Which one you sleep your life. But that's why Ada doesn't like to sleep on the sheet, because even when you're in thermal contact with it, that it draws more heat away from you. It's a better conductor of thermal heat. We'll talk about conductors more with electricity, because the same ideas will apply. All right? Now, when you have heat that changes, when it goes between materials, then you can change phase. And you'll know the three phases of matter. You'll need to know them for the test. And you'll need to know specific heat and latent heat and what that means. But the three phases of matter, of course, are solids, liquids, and gas. And a phase change occurs when you go from a solid to a liquid to a gas, or vice versa. And so this is just a diagram that shows I can go from a solid to a liquid and then to a gas. And then there's another phase of matter that is called a plasma. Y'all ever been to that really shady store in the mall where they sell gifts and stuff, like really shady gifts? Spencer's or whatever? You know what I'm talking about? And they have one of those glass balls that you can come put your finger to, and you know what I'm talking about? That's a plasma. And a plasma usually occurs in very, very hot areas, like, I don't know, the sun. Like the sun is mostly plasma. And when it's really, really hot, those atoms get moving around so quickly that the electrons and the protons are stripped away from one another. And that's what a plasma is. It's a completely ionized gas, where the electrons and the protons are stripped away from one another. So that also occurs at Spencer's, where the electrons and the protons get stripped away from one another. It's not really hot. It's stripped away in another way through the electrical energy. They just provide just the right amount of energy to strip those electrons away from the material inside the ball. So, solids, liquids, and gases, and then off to the side here I want to put plasma. And then off to here too, I'll write plasma. The enthalpy here, it just means the energy, don't worry about that. But as I go up, adding more and more energy to the substance. Originally it's a solid, it doesn't have much energy, because all those atoms, they don't move around that much, they're just sort of locked into place. But then as I add energy, I begin to break those bonds that are holding them in place, and it becomes a liquid. And then as I add more and more energy, it becomes a gas. And then if I add so much energy that it rips apart those protons and electrons, it becomes a plasma. So I'm going to write energy here. As the energy of the system increases. Now, the specific heat of a substance describes how much energy is required to change the temperature of an object. Is specific to the material, so different materials have different specific heats. Who's been to the beach before? Everybody probably been to the beach, right? Now, when you go in the afternoon to the beach in the middle of the summer, the sand is hot or cool? It's very, very hot, right? Sometimes you even need to wear shoes on the beach, but it can be quite warm. But the water, at the same time, is what? Is it hot or cold? It's cool, right? It's cold. It can be cold. So you have the hot beach and the cold water. But have you ever been in the morning time, in the early, early morning? It's like the sand is cool, but the water is relatively warm in comparison to the sand. And so I have these two materials that have different specific heats. Which do you think has a higher specific heat? The sand or the water? Which requires more energy to heat up? The water, right. And it actually turns out that the water requires more energy, not just because it has a higher specific heat, but also because there's just more of it. That the sand is, just the top part of the sand is heating up, but with the water it's churning around, and so you have to heat up all the water, and that just takes a really long time. But nonetheless, water does have a much higher specific heat than sand. Let's just write that on the side here. Water has a higher specific heat than sand, and voila, the beach is hot. While the water is cold. Because the sand doesn't require much energy from the sun to heat up. It has a low specific heat. But water requires a lot of energy from the sun to heat up because it has a high specific heat. Okay? Latent heat is the energy required to change phase. This describes how much energy is required to change phase. Usually the variable that we'll use for this is going to be the capital letter L. And by the way, the letter that we use to describe the specific heat is the lowercase letter c. That's for specific heat. All right? Now, calorimetry. You might have seen calorimetry if you've had a chemistry course here, or if you had chemistry in high school. You probably saw calorimetry. Q equals mc delta T. And I want you to have an understanding of how this works. So, calorimetry is the study of energy and how temperature and phase change. There are two formulae that we'll use in talking about calorimetry. These are both on your equation sheet, but you need to know them. You probably know them already. Q is equal to mc delta T, and then also Q is equal to m times L. And we'll have two subsets of equations for that second one. This one has to do, the one on the left has to do with temperature change, and the one on the right has to do with phase change. And in both cases, Q is the energy. It's the thermal energy. So it describes Q is the amount of energy required to change a mass of substance with a certain specific heat by a certain change in temperature. That first formula just tells us if I want to change 100 kilograms of water with a certain specific heat by 10 degrees Celsius, then I need this amount of energy. Q is the amount of energy that you need, M is the mass, C is the specific heat, and then delta T is the change in temperature. And this other formula describes the amount of energy that you need for a certain mass of material to change to a different phase. And we'll have two different formulae. This is just sort of the generic formula, but we'll have two latent heats. One is going to be LV, and one will be L, what do I use here? I'll have it here, LF. This is our latent heat of vaporization. And this is my latent heat of fusion. These will be very important later when we talk about how the body cools itself through sweating, because the body makes profound use of the latent heat of vaporization to make sure that it maintains a cooler temperature. The latent heat of vaporization, that's when a liquid goes to a gas. And the latent heat of fusion is when a solid goes to a liquid. All right, so if I'm looking back at that original diagram that we had up top, I'll come back to this. If I'm going back up here, I have my latent heat of fusion right here, and my latent heat of vaporization right there. That's my normal routes to go from a solid to a liquid, and then from a liquid to a gas. And you can go from a solid to a gas, but we're not going to talk about that. Sublimation, like when we get ice that deposits on like your windshield, that's going from a vapor to a solid. But we don't need to worry about that. Okay? Calorimeters. These are just insulated devices that measure the change in temperature from in a certain substance. So a calorimeter is an insulated container. Measure delta T, so you can calculate Q. If you did this in high school, your calorimeter probably looked something like this, a cup within a cup, because you know the best insulator is air, and that's why styrofoam ice chests are really good insulators, because not because the foam, but because of the little bubbles of air that they contain. And so the best insulator that you can get is just a cup within a cup, because you got all that air surrounding the cup. And then usually you had a lid on the top, and then you would put your thermometer inside here, and you could see how when you add two substances together, how the temperature changes. It looks at how the energy transfers between those substances. I have an audio clip I want to share with you. This is from an interview, from a radio interview, and they're talking about a bomb calorimeter. A bomb calorimeter, what they do is they take some substance and they put it into an insulated container like this, and they basically blow it up. So they put some energy into it to cause it to burn up, and then they measure what is the change in temperature, and they can account for the energy that they put in, but then they also measure that extra little rise of temperature about whatever they put in acting as a fuel. So basically they're putting a fuel source into the calorimeter and then measuring when it explodes, what is the change in temperature. And they do this for food. That's how they figure out how much energy is in food. So they'll take a sample of a foodstuff, they put it in a bomb calorimeter, they explode it, and then they measure what is the change in temperature. From that, you can figure out how much energy was in that food item. So let me pull it up for you. What is this? Give me just a second. I don't think any of you are dietetics, right? No dietetics in here? Anyway, these are things that people use to determine the amount of energy in food items. These bomb calorimeters, it's fairly common for them to do this. All right, so that's, oh no, one more thing. So this diagram that I show you, I want you to understand what this diagram is and how the latent heat of vaporization, the latent heat of fusion, and the specific heat is relevant to this diagram. This is a phase change diagram, and on the y-axis we have the temperature of the substance, and then on the x-axis we have the amount of energy. So you can think of, this shows energy per mass, but you can think of it, just think of it as energy. So this is the energy, Q, that I'm putting into the substance. And so let's say, for example, that I start with ice. That's what I'm doing down here. I start with ice. It's below the freezing point of water, which is at 0 degrees Celsius. So this is our freezing point. I'm at ice with minus 20 degrees Celsius. If I want to increase the temperature of that ice, I have to put energy in. And so as I move across the x-axis, I move up the y-axis. Put in energy, raise the temperature. But then notice, here, I'm putting in energy in, but the temperature is constant. And so what I'm doing here, in this point right here, as I move from 50 to 100 in my energy measure, is I'm changing that ice into water. So at this point, I have some ice and I have some water, but I'm putting in the energy required by the latent heat of what? Vaporization or fusion? That's my latent heat of fusion. How much energy is required per unit mass to change that material from a solid to a liquid? And so here, I'm putting in the latent heat of vaporization, or excuse me, latent heat of fusion, LF. Then at this point, I have water, and all of it is at 0 degrees Celsius. Did you know you can have water at 0 degrees Celsius? All right, a glass of ice water. Because the water and the ice are at about the same temperature. The water that you drink, that's not ice, right? That's water. But the ice is also 0 degrees Celsius or less. So I have this water at 0 degrees Celsius, and then I continue to add energy, going from here, where it's about 120 or so, all the way up to here at this point. So here I'm putting in energy, and I'm raising the temperature of the water. And so this is, at this point, the relevant equation is that Q equals mc delta T, that I'm raising the temperature by putting in energy. Then, at this point, right up here, I have 100-degree water, versus over here, I have 100-degree steam. So notice that between these 2 points, I have not changed the temperature because I have to put in energy. And it turns out I have to put in a lot of energy in order to get water to become a vapor. That is my latent heat of vaporization. This is my LV. So my energy required to change the water into steam is LV, my latent heat of vaporization. Notice over here I have 100-degree water, and over here I have 100-degree steam. You may have heard it said that steam burns are a lot worse than water burns. Y'all heard that said before? Even if they're the same temperature, if I have 100-degree steam, it will burn you a lot more than 100-degree water. And the reason is that 100-degree steam is much more energetic than 100-degree water. Even though they're the same temperature, it's not really the temperature that burns you, it's all the energy that your body takes in from that hot substance. And 100-degree steam has a lot more energy than 100-degree water because it has that extra latent heat of vaporization contained within the substance. Those electrons, or those atoms, are just moving around a lot faster than they were in 100-degree water. They can burn you a lot more. Okay? Okay, describe this graph for me. Latent heat of vaporization, latent heat of fusion, how the temperature remains constant even though I'm putting energy into the substance as I'm changing phases. You seen this diagram before? A few of you have? No, that's okay. All right. Any questions so far? No? Okay. All right. Let's see here. I have a couple questions I want you to answer. The Fahrenheit scale is based on the freezing point of water and which of these other temperatures? All right, let's stop at 20. Just 5 more seconds. Good job. B is right. Is based on the freezing point of water and the boiling point of water. And the Celsius scale is based on the freezing point of water and what else? It's the same, right? We just give different numbers for the Celsius and for the freezing and boiling points of water in the Celsius and Fahrenheit scales. But they're still based on those points of water. Oh, what happens when a frog's car breaks down? I mean, did you know that frogs drive? But what happens when their car breaks down? Don't be giving them a punchline. All right? What happens? You don't know? It gets towed away. All right, let's try this next one. Which of these changes in temperature is smaller? Fahrenheit, Celsius, Kelvin, or they all represent the same change in temperature? All right, let's stop at 33. 33. Good. A is right. What was the other one she'll put? D? Okay, I understand. Like D seems like it should be right because they're all 1 degree, right? Although I want you to, when we talk about Fahrenheit and Celsius, we put the degree mark here, but we don't do that with Kelvin. I don't know why. The Fahrenheit is the smallest. Remember, the Celsius and the Kelvin, these are the same. They have the same size of degree. They're just offset by 273. What is latent heat of fusion? All right, let's stop at 32. 32. Good. A is right. Awesome. Is the energy for a solid to become a liquid. That is latent heat of fusion. Remember, the latent heat of vaporization would be either of these. Either of those would be LV. All right, that would be latent heat of vaporization. Energy required for a liquid to become a gas or a gas to become a liquid. Though for a gas to become a liquid, you're actually taking away the latent heat of vaporization. Okay? From that material. Which contains more energy, or enthalpy? Water at 100 degrees Celsius, steam at 100 degrees Celsius, or they both contain the same energy? She's going to miss the joke, because y'all are probably going to do great on this one. You'll have to get her, like, tell her what it is later. All right, let's stop at 24. 24. Awesome. Megan? Watching you. What do you call a bear with no teeth? You don't know? A gummy bear. All right? Okay, so steam at 100 degrees Celsius has a lot more energy. Right, you saw in that graph how much energy it had to get before it actually turned into steam. It takes a lot of energy to turn a liquid into a gas. And we'll see that when our body sweats, the liquid turns to a gas, or turns to a vapor. And it takes all that energy away from our body. That's why sweating is such an effective means of cooling for our body, because of the latent heat of vaporization that we see when we go from a liquid to a gas. All right, so there are three methods for heat flow. There's conduction, convection, and radiation. Conduction requires, or excuse me, in conduction, you need thermal contact. And remember, when I say thermal contact, that doesn't mean necessarily that they have to be touching, but they have to be exchanging thermal energy in some way. Like with the coat hanger and the fire, that eventually the coat hanger will transfer the energy of the fire to you via, the material that you're in thermal contact with. We describe conduction with a formula, and as usual in this class, I'm not going to require you to calculate the rate of thermal conduction, but I do want you to know how the variables are related to one another, and it is on your equation sheet. So Q over T, that's heat over time, is equal to K times A times delta T, that's change in temperature, divided by D. So K is our thermal conductivity. Which has a higher K value? The sheet on Ada's bed or the fuzzy blanket on Ada's bed? Which has a higher K value? The sheet or the blanket? Which is more conductive? You're right. And that's why it feels colder. Because when you lay on the sheet, it's more conductive, and so it draws heat away from your body at a more rapid pace. And that's why it feels cold. Not because it's cold, but because it has a higher thermal conductivity. So that's what I tell Ada. Like, Ada, the sheet and the blanket are exactly the same temperature, but the sheet just has a higher thermal conductivity. So get in your bed and go to sleep. But she doesn't know. She just feels the sheet. I don't say it like that. Don't look at me like that. But she doesn't know. She just thinks the sheet is colder than the blanket. But really they're not, because they're in thermal equilibrium. They've been there all day, touching one another all day, and so they're exactly the same temperature. Okay?
So it's really bad for her to sleep on top of the sheet.
I don't really care what she does.
No, but I'm asking, like, for the example.
Well,
since the sheet's like a better thermal conductant.
no, it's better for her to sleep on the fuzzy blanket,
Okay.
right, because it's more insulating. And then she pulls another fuzzy blanket on top of her, so she's wrapped up in fuzzy blanket. But I don't like that for whatever reason, just because. I don't know. Okay, so K is thermal conductivity. sheet, low K, or excuse me, high K. Fuzzy blanket, low K. It doesn't conduct heat very well. A is the area. C is temperature, or change in temperature. And D is the distance between the two objects. Because I know what you're thinking. You're thinking, but you said they have to be in contact. But that doesn't mean that they have to necessarily be right next to one another. So I can think of this, usually in thermal physics, we think of, I have object A and I have object B. There's my two objects. And they're separated by some material. This is like the coat hanger between you and the fire. All right, that's how the two objects are in thermal contact. And this coat hanger, it has a length, a distance d, it has a cross-sectional area, A, and then just the material that it's made of. If it's metal, it's going to have a high thermal conductivity. If it's wood, like really that's the best marshmallow stick, is a stick. You make it sharp on the end and use that because it doesn't conduct heat hardly at all, right? A green stick, if you couldn't pull limbs off of 5 trees, right? Like that's bad. But a stick is better than a coat hanger because it doesn't conduct heat up to your fingers. Okay? I feel like y'all all ready to go camping now, aren't you? We're going out of town next week on Sunday morning. We always get, we live on the parade route, or like one block off. Well, actually, we're blocked in on parades. We're on 6th Street. That's the others? Yeah, so we live on 6th Street, and the parade typically goes on 5th and 7th Street. So we always get blocked in. So we usually try to leave during Mardi Gras. Because it's just crazy around our house. But this year, we're going to Percy Quinn State Park. Percy Quinn, have you ever been there? It's in Mississippi. It's Macomb, Mississippi. But we usually rent the cabin at Mardi Gras, so we're not camping. We're just cabin camping. But we'll still build a fire. Roast marshmallows and all that. Okay, so that's thermal conductivity between two materials. Convection, these others, there's no formula for them. But I just want you to know sort of what they are and how they work. Convection requires the flow of a fluid. A liquid or a gas. For example, a what? A convection oven, right? Convection oven is a good example. A convection oven is basically a normal oven, except it has what in it? It has a fan. And what the fan does is it moves that heat around inside the oven, or it moves the air that's heated up inside the oven around your cooking material, your bread or your roast or whatever it is you're cooking. So it's just a normal oven. It has a heating element down in the bottom and up in the top. But then it also has a fan. That's my fan. A fan that causes the flow of the fluid around your food. And that's why it cooks more efficiently and faster than a regular oven, because it moves that stuff around. You get not only heat transfer by radiation, which is how a normal oven works, but you also get heat transfer by convection. So let me write that down. Heat transfer by radiation and convection. And as I said, radiation is a normal oven. And then finally, radiation is the transfer of energy by light waves. We'll talk about the electromagnetic spectrum in a later chapter, but just for now, when I have something that's hot, it gives off infrared radiation, and that's how it transfers that energy. We'll talk more about that later. Alrighty? I like to do a thing midterm, and we're sort of almost midterm here. I like to do midterm student evaluation. So at the end of the semester, you'll give, what you liked about the course, what you didn't like. But this is your opportunity. I want everybody to do this. So take out a blank sheet of paper, just to write a couple of things, something that you like, and then something that you would change about the course. This is your opportunity, huh? Can somebody share a blank sheet of paper with the unprepared student?
You have your
Okay. Okay, something you like and something you would change. You don't have to put your name on it. It can be anonymous. And you don't have to write a book. You can just write a short sentence. Something you like and something you would change. And then you can just set them up here as you're leaving. And like I said, I won't look at them until you're gone. But if you think there's something you'd like to change, like you don't like the reading quizzes or you don't like this or that, I can do that mid-course, if it's doable. So take it as an opportunity. And then I have exams for Chriselle, Kenya, Christina, Kaylin. That's it. Oh. Y'all can get them afterwards. And Chriselle. Don't leave, Chriselle. Chriselle. Don't leave. Yeah. You're awesome. Yeah, you can go. Thank you. Thank you. Bye. Have a good day. Christine? Have a good day. Emily? Mallory. No.
Mariana.
Mariana. Okay. Oh yeah, have a good day. Oh yeah, have a good day. Your mouth.
Yes.
Yes. Maya, have a good day.
Me too.
Thank you. See? Good day. Dave, you're from Alabama?
No.
No, you just have the shirt. Over here, thank you. Yeah. Have a good day, okay? Yeah. What do you need?
I wasn't too happy about the grade.
Oh, yeah. Okay.
I was wondering if I can get like
Sure. Yeah, you want to come now or you have fun?
I can't.
Okay, give me just a few minutes. We'll meet. Okay.